Hello and welcome to today's topic 2.4, the precise definition of the limit. Mathematicians for a very long time have had a issue. Limits deal with very, very large numbers, sometimes numbers getting incredibly close to a number. But the issue with that is a lot of people have a different definition of what close is. For example, you might say that close to the number 0 might be something like 0.1. I might say it's like 0.001. So, what mathematicians have done to kind of streamline the limit is they've developed a precise definition of the limit. Previously, we've learned the intuitive definition of the limit, but this is the precise. So what this is really going to look like is the precise definition is let f be a function continuous on the interval around a, except for maybe at a itself. Then we can say the limit of f of x as x approaches a is L, denoted as limit as x approaches a of f of x is equal to L. If for every number epsilon there is a number delta such that 0 is less than and x minus a less than delta, then the absolute value of f of x minus L is less than epsilon. So, what this is going to look like. Epsilon is a value that you're going to add or subtract to L. So, it's really what's happening as you really get close to L. And we want to know those coordinates that you're using. So, as you get like really close, and let's say that we're up here. Nope, I don't want to do that. Then this up here is going to be your like upper epsilon, and that's what you're going to say is relatively close to your limit. Your delta is going to be the x value corresponding to your epsilon, or how far away that x value is from the a. So that's kind of where you get the absolute value of x minus a needs to be less than epsilon. This is just kind of telling you that, hey, for whatever distance this epsilon is, our x that corresponds to it minus a needs to be less than epsilon. All right. Continuing on, I have some practice problems for us. And I'm going to be honest. Epsilon, delta, precise definitions of limits can be one of the most challenging things to understand. It's true. But I think with enough practice, anyone can do it. So, I have a very simple one to start out with. So, we're going to start out by choosing an epsilon, and we are just going to say that our epsilon is going to be 0.01, either greater or less than that 8. Well, we don't really need to care about that. So, we are going to say our f of x here, which is 2x, and the absolute value, minus 8, because it's the precise definition goes, f of x minus L, absolute value, needs to be less than epsilon, minus 8, absolute value, and needs to be less than 0.01. All right. What do we want to do with this? Well, we need to find a delta. And delta is given by x minus a, an absolute value, is less than delta. So, we are going to take this delta, and we're going to plug in some values. So our a is just what our limit is approaching. So we get x plus 4 needs to be less than delta. How can we find delta if we are given this expression? Well, let's try something. Let's try factoring. So we are going to get 2, and we're going to put the 2 in absolute values, times by x minus 4, and the absolute value is less than 0.01. Now what can we do? Well, 2 is always a positive number, so the absolute value can go away, so we're just left with 2. X minus 4 is less than 0.01. Well, we're getting really close to something that looks like this delta expression up there. So what we're going to do is we're going to divide both sides by 2, and we are going to get 0.01 divided by 5, or sorry, divided by 2. And as my math teacher always yelled at me for, he hates decimals and fractions. So we're going to convert that into a decimal of 0.005. All right. Is less than 0.005. And now what you'll see is this x minus 4 and this x minus 4 are the exact same. So as thus, since they're both less than this 0.005, delta must be equal to 0.005. Or rather, we really want our delta to be less than 0.005. But I digress. Less than or equal to. I'll leave it at that. Okay, the limit as x approaches 1 of x squared plus x plus 6. Well, once again, let's find a new starting point. We're going to start out by defining our delta, as that's a good place to start. So we want x minus 1 to be our delta. It needs to be a less than delta. And then we have this next part, this next function that we need to do to find our epsilon. So we know epsilon is given by x squared plus x plus 6, which is just f of x, minus the L is less than our epsilon. And let's say our epsilon is once again 0.01. Just makes life easy. 0.01. Okay. So what we're going to do, we're going to start out by condensing this a little, so we get x squared plus x minus 2. Then let's factor it. So we are going to get a 1 and a negative 2. We want something that is going to add to negative 1 and something that's going to multiply to negative 2. So let's just do 2 and negative 1. Using our properties of absolute values, we know that this is going to just be x plus 2, x minus 1, and is going to be less than 0.01. Look at that. We have our x minus 1. But there's an issue. You can't divide a variable in an absolute value. So what we're going to do is we're going to say, well, we are looking at the range. We are really looking at this interval of this function, this f of x, from 0 to 1. So because we are in the interval, and I actually lied, I meant to say 0 to 2. From 0 to 2, the maximum value, and you might be asking, why do we want the max value, not the min value or another value? Well, if we did the min value, it would actually give us a very, in fact, a over approximation for our delta compared to our epsilon. So we want to do the max value to get as close as possible because the max value of the absolute value of x plus 2 is going to be 4. So now we can rewrite this really as 4 absolute value of x minus 1 is less than 0.01. Well, we're getting there to the home stretch. We got absolute value of x minus 1 less than 0.01 divided by 4. And as my old calc teacher says, can't leave decimals and fractions together. So in this case, I'm going to do something just a small bit different. And I'm just going to call this 1/400th. As that's also something you can do. So, because this expression and this expression are equal, we now know that our delta needs to be 1/400th. And that, my friends, is the basics of the epsilon delta function. But it does get a bit more complicated. One-sided limits. So, the limit as x approaches a from the left of f of x is equal to L. If a is a minus delta less than x less than a, then there is an epsilon such that f of x minus L is less than epsilon. Alright, and then for a right-handed limit, the limit as x approaches a from the right of f of x is equal to L. If a is less than x is less than a plus delta, then the absolute value of f of x minus L must be less than epsilon. I don't believe I want to do this problem. I believe this problem has a very ugly solution, so I'm not going to do it. If you wish to try it, you can. But for my knowledge, it is unsolvable. JK, it's not. That just takes a lot of time. So I want to also go over infinite limits. So an infinite limit is, once again, a limit that's going to go to... Well, the limit as x approaches a is going to go to infinity. So, we say that we define a new number m. So, for every m is greater than 0, there is a delta such that x minus a is less than delta, then f of x is greater than m. So, what this really looks like is we have this m value, and our deltas, we want to make it such that our deltas are a minus delta. Sorry. But our deltas are like delta away, but it makes it so all of our x values are greater than m, or f of x values are greater than m. And similarly for the negative infinity as x approaches a, we have absolute value of x minus a is less than delta, then f of x must be less than n. And n is just a number like down here defined, and once again it has the same epsilon delta. Okay, and I have a little practice problem for us. So this practice problem is going to go as such. We want to first find out, well, this limit's going to infinity, so we're going to use our infinite one of our infinite definitions. So we are going to say that, give me 1 second, sorry. Okay, so we want an epsilon, or sorry, a delta, such that the absolute value of x minus a is less than delta, and we want an m to be less than f of x. So I'm going to say Rm I want to be 1,000. So m in this case is kind of like our epsilon, so we just want epsilon to be less than f of x, which is 1 over x minus 2 squared. So, how do I want to solve this? Well, I want to start... Well, I want to first actually make sure that over here is defined. So, I want to start out by taking the reciprocal of both sides of this. So we're going to raise both sides to the -1 power, and one of the properties of inequalities is that they are going to switch signs when we do this. So is going to be less than x minus 2 squared. Alright. This hasn't done us very good, but I think we can still work with this. Now, I want to take the square root of both sides, but because I want the positive or the negative square root, I am going to say that this is going to be plus or minus the square root. So we are going to get a 1 over 1,000 is less than x minus 2. And I'm also going to now define a new portion of this that is going to be, sorry, negative 1,000. Alright. Now what? Very good question, you might ask. Well, let's add 2 to both sides. Well, actually, no, that won't do much. Let's see. So, what you may have noticed is this is actually in the form that we want. I just got very confused for a moment. So, we really want our delta, and this right here is really just, we don't have to worry about both those. Since we're dealing with the absolute value. Or wait, no, this one doesn't deal with the absolute value. But we don't have to worry about both of those, as the delta is really just saying add or subtract. So I think because this value can just be directly plugged in there, and besides that, it's like saying the absolute value, we can take the absolute value of this. It's going to remove this inequality on this side in general. So we will now get the inequality of the absolute value of negative 1,000 is just 1 over 1,000 is less than x minus 2. And we now have our delta. So our delta is 1 over 1,000. Surprisingly enough. Alrighty. Well, continuing on, I just have one last topic I'd like to talk about. And is, when does the precise definition not work? And it's going to be frank. It's the exact same as any other limit. If there's a discontinuity, such as this one. In fact, this discontinuity is called a jump discontinuity, but we'll talk about that in the next video. Or an oscillation. And the reason why is whenever you, let's say I wanted to estimate whatever this point here is A. Well, I need to choose an epsilon that's like really close to A. Or, yeah, an epsilon. And even though that works on one side, it doesn't work on the other because of the gap. So that's why it doesn't work. And for oscillations in general, like, I mean, if I wanted to zoom in on this oscillation, so I'm going to real quickly delete this and, like, zoom in. Alright, so now that I've zoomed in, we can see that this is still like incredibly crunched. And in fact, if I zoomed in again, I would see that it's even more crunched. What I'm trying to get at here is no matter how close you get to like the point where it's oscillating, no matter what you do, it's going to fail to exist because it's not going to approach a certain point. It's going to oscillate around the point. But that's all I have for you today. I honestly encourage you to go find more work on epsilon delta. I'll probably have a YouTube short going over some more multiple choice questions dealing with it. I hope you all have a wonderful rest of your day and enjoyed and found this informative. Goodbye.